Electromagnetic effects, the assignment question 19 will begin with question 19. The question 19 is basically about the force on a wire which is placed in a magnetic field. So what will happen when a current carrying conductor, a wire which is carrying a current, is placed in a magnetic field? If because of the current carrying conductor in a magnetic field, it experience a force. So if the wire experience an upward force, the magnet will experience a downward force, so the reading on the balance will increase. And opposite will happen if the wire experience a downward force, the magnet, according to Newton pair forces, the magnet experience an upward force, which is placed on the balance, so the reading on the balance will decrease. So a student placed two magnets on a holder, as you can see, so that the north pole of one magnet faced the south pole of the other magnet. The arrangement was placed on a sensitive balance calibrated to measure force. Student held a part of a closed loop wire between the magnet as shown in the photograph. The next part, when the student moved the wire quickly down, the reading on the balance change. Explain how the reading of the balance change on the balance change, and it's of 6 marks. First thing, we don't have according to the question, we don't have any battery here. So if we don't have a battery, like if I draw, we move the wire downward between the magnetic pole. One side is a north pole, other side is the south pole, and it is moved downward. So as a result, when it is moved downward, what will happen? There will be a change in the magnetic field, or a magnetic flux, you can also say, or magnetic flux linkage. So whenever there is a change in magnetic flux linkage, there will be an induced EMF or there will be a voltage in the wire. Wire is not connected to any source of the supply, like it is not connected to any battery or a cell. But because you move the wire downward, it causes a change in the magnetic flux linkage. And whenever there is a change in magnetic flux linkage, what will happen? It will induce or it will produce an EMF. Now, which direction the current will produce? Because wire is moved between the magnetic pole, produce a change in magnetic flux linkage, which induces EMF or produce EMF. And because it is a closed loop, like it is a closed circuit, if we have a closed circuit like wire is connected, so then there will be a current. Which direction there will be a current? How we can work out the direction of the current? We can use a right hand rule to identify the direction of the current. Now, if the wire is moving downward, like this is the motion of the wire, this is the direction of the motion of the wire. As we already discussed the Lenz law. What is the Lenz law? According to a Lenz law, the EMF induced always oppose the change in magnetic field. So if the wire is moving, if the wire or a direction of a motion of a wire is upward, what will be the direction of the motion, direction of the force on the wire because of change in magnetic field? Because according to Lenz law, EMF induced always try to oppose the change. So if we are moving the wire downward, the force on the wire will be upward. Why the force on the wire is upward? To oppose the change. If a wire was moving upward, then the force will be downward to oppose the change. That is the Lenz law of electromagnetic induction, that EMF induced always oppose the change in the magnetic field. So if there is a force on the wire upward, which direction the force on a magnet according to Newton pair force? Forces always act in pair, and pair force are characteristic that they are same type, acting in the same line, acting on the same time, acting on two different objects, two different opposite direction. So the force on the magnet will be downward. So already there is a weight of the magnet and there is a downward force because of a change in magnetic field. So what will happen to reading on the balance? The reading on the balance will increase. Is it clear? Should I repeat about this example? Is it clear to everyone? So we use the Faraday because we don't have the north and the south pole, so we cannot have exact direction. So I will repeat. Look, what happened? You have a magnet and there is a wire which you are moving it downwards. No need to mention left or right. That was I was giving an explanation. But how to structure this answer? How to say the answer? You will say the wire is moving downward. Okay. So this is the direction of the motion of the wire. This is the direction of the motion of wire. Because of the motion of the wire, like as a wire is moving downward, as a result, there is a change in the magnetic flux linkage. Or magnetic flux linkage. And when there is a change in magnetic flux linkage, according to Faraday's law, you will mention according to Faraday's law, it will induce EMF. And whenever there is a voltage, and if we have a closed circuit or a closed loop is there, like wire is connected one end to another, so it will also produce a current. So as a result, there will be a current. And according to, so this is 3 marks. Then according to Lenz's law, the EMF induced always try to oppose the change. Like mentioning a Lenz law, that will always try to oppose the change. How it can oppose the change? If a wire is moving downward, what it will try to do? It will try to apply an upward force because of a change in magnetic field. So wire will experience an upward force. If a wire experiences an upward force according to Newton pair forces, Newton third law, that there will be a force on the magnet which is downward. Because Newton pair forces that if the wire experiences an upward, the magnet experiences a downward force. As a magnet experiences a downward force, so there is a force on the magnet downward and the weight of the magnet is also downward. So the resultant force or the downward force increases. So the reading on the balance will also increase. Is it clear to everyone now? Okay. So you don't have to mention left or a right hand rule because you don't know which pole is north and which is south. So that's why it cannot be done in this manner. Like I don't know which side is north and which side is south. So I cannot use my any rule left or a right to find the direction of the induced EMF or a current or even the force on the wire. But we judge that by the motion of the wire, we can judge that the force should be upward because according to Lenz's law, it will always try to oppose the change. So if it was moving towards the downward, it will try to move it, push it upward. If it was moving upward, it will try to pull it downwards. So a voltmeter is connected across the end of a second wire. The student moved the wire vertically down between the magnet at a constant speed. The potential was observed on the voltmeter while the wire is moving. Calculate the maximum potential that could have been measured, like the induced EMF. The length of each magnet, the height of each magnet is given. The magnetic flux is also given and the vertical speed is also given. Look, why it is important to know the length of the magnet and the height of the magnet, because like if I say the length of the magnet is 34 millimeters and the height of the magnet was 20 millimeters, so this is only when I move the wire through this magnet through this area, so how much area it will sweep. So it will complete, like if it start from here and finish till this point. So how much area it will sweep? Because we want an area for a magnetic flux linkage, we want an area. So that is why the length and the width are important. Because this formula for n phi, the formula for n phi, phi is what B dot is, so it is NBA. N is a number of the turns, which we have only one here. B is the strength of a magnetic field, which is already given. And A is the area, which it will sweep. And the induced EMF is equals to minus delta n phi over delta t. And we have the vertical speed. So using a vertical speed and using the height, we can work out how much time it will take to cover this 20 millimeter. Because it was moving at a speed of 2.2 meters per second and it will cover this 20 millimeter, the distance. So we can work out how much time it take to move through this. So let's solve like with the values. So the area which it will cover, because we need how much area, because for the magnetic flux linkage, we need an area. So the area which it will cover or it will sweep or swept off, it will be the length which is 34. So we'll convert into meter. So 34 into 10 to the power minus 3 multiply by 20 into 10 to the power minus 3. So we got this as 68 into 10 to the power minus 5 meter square. That is the area which it will cover. 6.8 exponent minus 4. Okay. 6.8 exponent minus 4 or 68 exponent minus 5. That's then how much time it will take? Because it move at a constant speed. So speed is distance divided by time. So if I need the time, it will be a distance divided by speed. So distance which it cover, because that is the vertical height it covered. So that was 20 millimeter, 20 to 10 to the power minus 3, and it was moving at a speed of 2.2. So we got 9.1 into 10 to the power minus 3 second. That's the time interval. Then I can work out the flux, or I can directly substitute in this. And they just ask her for the maximum value. They did not say whether it is positive or negative. So we just need a magnitude. So you can solve this question by two ways, like considering initial as zero, so final will be maximum, or considering initial is maximum, so final will be zero. So both ways it is acceptable because we just need the maximum potential. It's not about the sign, like maximum potential or a voltage it can be measured. One of them will be zero. So let's say final I am taking a zero, so it will be n phi. What about n? It's just a single wire is there. So n is equals to 1 and phi is B dot A. The strength of magnetic field 0.35 Tesla multiplied by cross-sectional area, which is 68 into 10 to the power minus 5, divided by the time interval, which is 9.1 into 10 to the power minus 3. So we'll get an induced EMF. What's the answer for the induced EMF? 0.35 into you can take any one of them zero. Like what I consider, let's say it was between the magnetic poles initially at this position and I moved out. So that's why I took final as zero. Or you can also do like you can consider initial as zero and at this point the maximum will be there. As we just need a magnitude, that's why any one of them. What about number of turns? It is one. It's a single wire is there. It's not like having loops. That's why n is equals to 1. So in this example, you can consider, as they did not mention, it's like it's up to you. Any one of them you can consider. You can consider initially it is in a magnetic field, then you moved out, or initially it was outside and then you moved in. So 0.026, so 0.026 2 volts. That will be the induced EMF. And we should write the answer in like, because the minimum value which was given to us in two significant figure. So this answer should be in two significant. So I should write as 0.026. Is it clear, this example? Any doubt in this? Okay. Why we always... No, the answer, the final answer depends on the values which are given to you. Look, when we decide the final answer, we check what values we use for a calculation. Two significant, two significant, two significant, two. So the minimum number of significant figure which were given in the data were two. That's why the final answer should be either a minimum number of the significant figure which is given in the data or minimum plus one. Like I can give in three significant figure as well, but it should be at least two because that is the data is given in two. Data is accurate to two significant figure. That's why my final answer should be in two significant. But let's say if it was like 340, 200, 0.351 and 2.21. So all three now, then I will write the three significant. Or some of them are two and some of them are three. Then I will write the answer in the minimum number of the significant figure. Moving on to the next question. In question 20, a particle with a charge q with a momentum p follows a circular path of a radius r. The magnetic field is perpendicular. We have to drive equation. So if the magnetic, like a particle is there, which is having a charge q, it's moving in a circular path, any circular, like maybe clockwise or anti-clockwise. So it means whenever object move in a circular path, the force which is acting, that is a centripetal force. And centripetal force should be equal to magnetic force because object is moving in a circular path. So the magnetic force and the centripetal forces are equal. So centripetal force is equal to magnetic force. What is the centripetal force? It is mv square over r. And what about the magnetic force? It is qvb, where q is a charge, which is capital Q. V is the speed, and or bqv you can also write. Order is not important because it's a multiplication. So bqv. So v is same for both sides, so it can cancel out. What is mv? mv is mass into velocity, which is a momentum. So I can write p. Here I can write r. So bq. So if I need r, like if I make r as a subject, so this will be cross multiply. So p divided by bq will be equals to r. So that's how we got the formula. Is it clear? This is a short derivation that this magnetic force will be, because when it is causing a circular motion, the magnetic force will be equals to centripetal force. A particle, the particle is an alpha particle with an energy of 5.4 mega electron volt. Calculate B. We have the formula is already here. R is equals to P divided by BQ. So R is equals to P divided by BQ. The particle is an alpha particle with a kinetic energy of 5.4. So there is also a relation between a kinetic energy and a momentum. We don't have to derive this relation, but it is like I will just derive to give an, like, so you'll understand that kinetic energy is half mv square. If I multiply, this is not part of the question. Like, I'm just deriving a formula. So if I multiply both sides by m, so this will become m multiplied by kinetic energy Ek. This m is multiplied by m, so it will become m square v square over 2. What is m square v square? Is a momentum square. So m into Ek is equals to p square over 2. If I need momentum, so it will be 2 into m into Ek is equals to p square. But if I need p, it will be equals to under root. So actually, momentum is equivalent to what? It is 2m into Ek. If I know the kinetic energy, I know the mass of particle, multiply by 2, take a root, I'll get the momentum. Because what I need in the question, I need B. So if I need B, the formula, it's the same formula, P divided by R into Q. R is already given, this R is given. The mass of alpha particle is given. Q is the charge of alpha particle. What is the alpha particle? Alpha particle is 2 proton and 2 neutron. So we know the charge, the constant is there. You can also use P is equals to mv, but the problem is first using a kinetic energy. Using a kinetic energy half mv square, you have to find V. And then after finding V, you will substitute with mv to get the momentum. So you can also do that method, or this is a direct formula. If I know the kinetic energy and the mass, I can find the momentum. But 5.4 mega electron volt, you cannot substitute directly. Why? Because energy should be in joules. So first part, what we have to do, we have to convert this kinetic energy in joules. So first, mega means what? Mega means 10 power 6. So first we convert into electron volt. So this will be equivalent to 5.4 into 10 power 6 electron volt. 1 electron volt is equivalent to what? 1 electron volt is 1.6 into 10 power minus 19 joules. So we multiply this by 1.6 exponent minus 19. So 5.4 into 10 power 6 multiplied by 1.6 exponent minus 19. This will give us the answer in joules, the kinetic energy in joules, which is equals to, you can annotate on the screen for any values. So this is 8.64 into 10 power minus 13. So this is energy, but that is in joules. Now we need the momentum first. So momentum is what? Under root 2. The mass of the alpha particle is given 6.64 into 10 power minus 27. And the energy of alpha particle is 8.64 into 10 power minus 30. When you multiply, you will get the momentum, kilogram meters per second. Which is 1.07 into 10 power 19 minus 19. Okay, so we got the momentum. So now we have the momentum. And what about Q? Because alpha particle 2 proton 2 neutron, so and charge of 1 proton is 1.6 exponent minus 19. So if I need B, it will the momentum 1.07 into 10 power minus 19 divided by R, the radius, which is 0.096, multiplied by charge. It will be 2 times 1.6 into 10 power minus 19. So that will give us the strength of a magnetic field, which is 3.48 Tesla. So here we wrote answer in three significant figure. I can also write as 3.5 Tesla. Normally, as I mentioned, we check like this is two significant, this is three significant, this is two significant. So we can write the answer either the minimum, like least significant, or least plus one. Like I can write the answer in two or three. Is it clear? This one? So this was questions related to the electromagnetic effect.